Generate statement. The generate statement are concurrent statements which embedded concurrent statements which can be interpreted as a circuit part. There are two types of generate statements. The for generate statements, which is used to create a circuit by replicating the hardware part, and the if generate statement, which is used to specify whether or not to create an optional hardware part. The generate statements are especially useful for the parameterized design. The for generate statement syntax is generate label, in loop index, in loop range, generate, and the concurrent statement. The concurrent statement generally is an instantiation of a component and is replicated as many times specified in the loop range. Soon we will see an example that should clarify better the syntax. Then the generate statement is closed with and generate label. The if generate statement syntax is generate label if condition. If the condition is true, the generate statement is instantiated. Then the and generate label. The if generate statement allows you to implement the concurrent statement inside the generate. Just to have a parallel with the software languages, if generate statement is very similar to the define in the C language. Let's see an example of generate. The classical example is at the shift register. We use a single flip-flop with clock reset input and D and Q, and we need to instantiate this flip-flop in order to generate a shift register. So the first input is the first of the chain and the output is the last. We have a chain declared from 0 to n, where n is the depth of the shift register. In this case, when n is 0, we connect input to id, I underscore d. When input is n minus 1, we connect n minus 2 to n minus 1. And the output n is the output of Q. Let's see how to implement this shift register. With the for generate in this case. Start quartus and create a simple project. Test 1. Open. Next. Stratix 2, okay. Technology is not important. We have an error. The error is Quartus cannot find test 1 because we have to select the top level. This is the top level. And run. we want to generate a shift register with the n equal to 8, so we should have 8 flip-flop. In fact, total register are 8. Let's see the RTL viewer, and as you can see, we have 1, 2, 3, 4, 5, 6, 8. 1, 2, 3, 4, 5, 6, 7, 8 flip-flop. This is the RTL viewer. Let's see the post layout. So flatten next netlist. Zoom fit 1, 2, 3, 4, 5, 6, 7, 8. This should be a flip-flop. Okay, let's see the same example using an if generate. In this case, we have the same D flip-flop, and in this case we connect for 0 to n-1 when E is equal to 0, so the first flip-flop we want to connect E to the input, and the output is plus 1. So E and W chain of 1. Then when E greater than 0 and less than n-1, we have the same syntax. The last, when is equal n-1, we have to connect the last one, n-1, and the output is Q. Let's see if we have the same implementation on Quartus. So, start another instance of Quartus. Let's generate another test 2, and copy the path, new project wizard, test 2, okay. In this case we need this one and this one. Next, same technology, finish. Set top level, and as you can see, in this case we have the if generate. So let's compile. Even in this case you see that we have 8 register, and RTL viewer. The RTL viewer is the same. The post this is test 1, the test 2, the post layout netlist. Let's flatten the netlist and zoom fit. 1, 2, 3, 4, 5, 6, 7, 8. Even in this case, we have the same pose layout netlist. So the two RTL implementation are totally equivalent.